Just let me know in simple terms, how does this CHP-based multiport DC converter differ from the traditional transformer-based charging system? And tell us more about your work in simplified way.
Sure. So what happens is essentially there is a key point in electrical, right? So when you send power in electrical terms, it is there is a voltage and there is a current, right? So the power is basically voltage multiplied by current. So if for the same amount of power, if you keep the voltage high, then the current will be low, right? and and current is what flows through your wires, right? So if the current is high, then there is resistive drop in the wire and you are going to lose power, correct? So that is why you see that our transmission of power from a large thermal power plant or this happens at very high voltage, right? And then you have this transformers which steps it down, keeps on stepping it down and bring it to 230 volt, which we actually access as a utility, right?
Okay.
So but the 230 volt happens very near to our home, right? Because we don't want to send bulk power at low voltage, so the current will be very high and there will be a lot of loss, right? So this is essentially the idea. So now what is happening is, now I will come to the context of electric vehicle charging, right? So now in very normal terms, electric vehicle charging, what happens is that in the electric vehicle, the petrol tank is your battery, right? And the petrol or the energy is in terms of charge. That is there, you charge the battery, correct? So
Okay.
you transfer power into the, it is same as filling your tank with petrol, right? But the thing is that there what happens is, now the how fast you are going to send the charge into the battery depends upon how powerful your charger is. Okay. So the thing is that, so if your charger is powerful, then to send the same amount of charge it will take less time, right? So now what's happening today is, it about with the fast chargers which are there in the market, still it takes about 1 hour to charge. If you have
Right.
noticed, you will see
Yes.
this 50 kilowatt chargers everywhere, right, in the charging stations, and which we understand is quite inconvenient, right?
True.
Right, so because you can fill your petrol car in maybe less than a minute, right? Maybe 2 minutes you fill it, right? And compared to that, 1 hour is too
I
long.
have the EV car and it takes
Oh,
time, right?
so
Yeah.
you know this, right? So
Yes.
you know this
Mm.
perfect.
Mm.
So now what happens is that if to charge faster, you need to actually transfer the same amount of charge at a higher current or a higher power,
True.
correct?
Mm.
So now what's happening is, now I will in this discussion I will try to give you the baseline. Say for example, this, like our charger for the mobile phones are like 20 watt in that order, 20, 30, 40 watt. Or if you go to your home, everything put together, it will be like a kilowatt, one
Yeah.
kilowatt, right?
Yes.
So now in your four wheeler, typically the battery that is there, we talk about that the capacity of the battery as kilowatt hour, right? That
Mm.
is sort of the energy. So we say it is 50 kilowatt hour battery, right?
Mm.
So now if you charge with a power of 50 kilowatt, that is what we call 1C charging, it will take you 1 hour to charge that battery, right?
Right.
So now if you use a 100 kilowatt charger, it will take you 30 minutes approximately,
Yes.
right? So that is basically the idea. So the thing is that if you want it to happen say in 10 minutes,
Mm.
you need a 500 kilowatt charger,
True.
correct, to do that in 10 minutes. Now what happens is that now you just think about it, that we are slowly going there. So now what are the challenges why we do not see a fast charging like that?
Mm.
There are two challenges. First is the battery technology
Mm.
limits you how fast you can charge, right? But people are working, all over the world to improve this charging speed at
Mm.
which you can charge the battery. It depends upon the battery chemistry, and it is improving, right?
Right.
And the other side is that you also need this charger to go high power, right?
Mm.
Now you just think about it. If I'm going for 10 minutes charging my 50 kilowatt hour battery, I am talking about a 500 kilowatt hour, 500 kilowatt charger. And what does that mean? 500 kilowatt is a power that is delivered to 500 houses, right?
Mm. True.
It's an enormous amount of power, right?
Yes.
So now typically what happens is that you cannot suddenly draw 500 kilowatt from the grid. The grid will crumble, right?
Mm.
And that is why what happens is many of these charging stations today, they also have a battery reservoir, right? So
Right.
that's not the vehicle battery. So you slowly keep charging the battery from the grid, not at a high power, but you
Right.
keep on charging it. And whenever there is a car coming to charge, you can charge it. Even transfer that energy from the storage battery that you are holding there. It is
Mm.
like having a petrol pump, in a bigger, storage tank
Right.
at
Right.
your
Got it.
facility,
Mm.
right? So now the thing is that what happens is that, but even if you have that storage business, right, still you need to draw high amount of power, right? So now whenever you draw a power which is like a half a megawatt, what we 500 kilowatt, like 1,000 kilowatt is 1 megawatt, right? So you see typically the big buildings, hospitals, right? They sort of draw that kind of power, and that power again will not be supplied to you at 230 volt or 440
Mm.
volt, right? Because the current is going to be enormous, right?
Mm.
So there what happens is that they will supply that at 11 kilovolt in India,
Okay.
right? And
Okay.
that is where you see that, and there will be a transformer. I think you have seen this, like there will be a small yard with a transformer and the stone chips
True.
around, right?
Yes. Yes.
And so what happens is that that transformer is going to step it down to 400 volt or 410 volt, 50
Mm.
hertz, three phase, which is in India, which is equivalent to 230 volt single phase, right?
Mm.
And that goes to the charger. So today what happens is you have that transformer in every charging station that drops it down, makes it 400 volt, and then you connect that using a charger, right, to your car battery. That's
Mm.
what is going on today, right? So now if you think about it, like there are two problems with in this model. One is that this transformer is pretty huge and big, right?
Mm.
And it is mainly copper and iron, right? So it has a huge material footprint. It is expensive,
Mm.
right? And how much copper has gone up in these days. Like people are
Right.
talking about, instead of gold buying copper, right?
Mm. True.
So the thing is that so it is huge and expensive. And another problem is that when you have something like this, right, like then you have a 400 volt and then you have multiple chargers, right? So you have a 400 volt bus that's also drops a lot of power because
Mm.
you're taking that and you're circulating that, right? So there is where our invention comes in. So what happens is that we directly connect to the medium voltage at 11 kV.
Mm.
Of course, we have a transformer inside because you need this kind of transformer, what you call the so-called galvanic isolation for safety.
Mm.
But we realize those transformers at much higher frequency, right? And not at 50 hertz, using power electronics, innovations in power electronics, right? So you must have also noticed that these days, see your chargers, like laptop chargers, used to be quite bulky, 10 years back, but now you see this very small fast chargers, right? Even
Right.
in Amazon, you will find this gallium nitride based, GaN based fast
Mm.
chargers, right? Very
Right.
small, high power. These are all possible because we can go to high frequency, right?
Mm.
If you can go to high frequency, you can reduce the size, right?
Okay.
So our innovation does that, right? And it basically removes that large step down, what we call that 50 hertz transformer, with
Mm.
high frequency transformers internally, right? And then it creates multiple ports at the output, so that and they are isolated from each other, so that each car can be charged
Right.
parallelly, right? So now what happens is, just one second. Yeah. So now what happens is that so with our innovation we can remove that connection, right? And now and also what happens is that when you in the previous model when you are taking the power slowly and charging your storage, which is locally placed in your charging station, then you have to again reflow that charge to the car battery, correct? And so the thing is that there is there are multiple power conversion stages involved.
Mm.
And
Right.
if you do this multiple stages the way today it is done, right, that is inefficient. And see, we are talking about in an aggregate it's a huge amount of power. So even if you can improve things by 3-4% in efficiency terms,
Mm.
that means a lot smaller carbon footprint, and it is cumulative. The energy is
True,
power
true.
into time, right? So 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 the thing is that so that is what, so we also in this innovation we also address that issue, right?
Mm-hmm.
We cut down on the number of stages in which power has to flow from the
Mm.
storage battery to this other battery. And so these are basically the
So,
innovation.
sir, in continuation to this, I want to ask what are the key hurdles in scaling your prototype from 1.2 kilowatt to megawatt level?
Yes, 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 yes. So now the thing is, I will tell you that this is the concept that is known as solid state transformers, right?
Mm.
Where you are using semiconductors more to convert, the change the power from at a voltage, high voltage to low voltage level. So the real challenge is if you look at the traditional system where
Mm.
you are going just you are doing the step down from 11 kV to 400 volt, and then
Mm.
your charger is just if you just think about one car with one charger, that charger is taking 400 volt and pumping the charge into the car battery, right?
Mm. Mm.
Now, in this system, the transformer is highly efficient,
Mm.
right? So, because we are working with this 550 hertz transformer for last 100 years or more than that, right? From when we had the electricity. Now, these are pretty efficient, but what happens is that when we do the power electronics to change the frequency, right? So that power electronics requires more semiconductor devices, right, to do this job, right?
Right.
So now the thing is that in this kind of converters, you are going to have large number of semiconductor switches or devices, right? So there are two issues with that. The first is that things actually gets expensive if you just built one, right? The copper is expensive, silicon always it is coming down, right? So that's the
Mm.
whole idea of uh, processing things with silicon rather than copper, right? But the thing is, to have the economy of scale you need to build a lot of them initially,
Right.
right? So that's one point. And the second point is that when you do a power conversion like this where you use power electronics to increase the frequency that your transformer sees to reduce the size, like we are doing it at 100 kilohertz, let's say, not 50 hertz, which dramatically reduces the size of your transformer internally. So there what happens is that you end up getting more power conversion, doing you are doing more power conversion, and that end up into more loss, right?
True.
So the thing is, even though this concept is known, it is not new, but people are working on to figure out how can I also meet an efficiency of the regular or the state of the art, right?
Mm-hmm.
So now our research shows that we will be able to actually meet or even beat the loss that happens in the traditional system, right? But now the thing is that it has been done on a prototype scale at 1.2 kilowatt, which is a toy, right? But so there are a lot of challenges in scaling that idea, right, into a megawatt scale system, and achieving the same kind of efficiency. But what happens is that we have done the because we have verified this in a smaller prototype, and our calculation says that it will be actually possible to scale it at that power level. And what is happening that this work is jointly done with Delta Electronics, which is one of the premium power electronics company, are have a big footprint in EV
Mm.
charging space. So we are actually working with them. They are also part of this. They were co-authors in this paper. And so what we are going to do is we are currently building a lab in IISc, which is a center of excellence, which is heavily funded by Delta Electronics, right? So it is going to be a Delta IISc center of excellence on medium voltage power electronics.
Mm-hmm.
And the thing is that the lab is already in place. I mean, it is about I think 3,000 square feet space IISc has given us, and they
Mm.
have also invested in putting up the laboratory. And there our plan is to, it is not a megawatt, but it is somewhere between 250 kilowatt to half a megawatt. We
Okay.
are going to actually build this, and we are going to test this on car emulators. Like, you can emulate the car load using some other electronics. So Delta builds those systems to
Okay.
test their EV batteries,
Mm-hmm.
EV chargers. So the Delta is also providing us those emulators with which, we will be actually testing and before going to field test, right?
Okay. Okay.
So this
So
is a
how
major project. Yeah.
okay,
Mhm.
how soon could we expect to see a commercial pilot or field trial of this technology?
Yes. See, we believe that the lab is going to be ready in another a month, I think, and we are going to do inauguration. So I will let you know if you're interested to pick up
Sure.
that time, right? Cover us. And we believe that from that point, we are doing work. It should take about an year
Mm-hmm.
for us to get there and do it. And I
Okay.
can tell you that today at this scale, there is only two prototypes have been built. One is in an academic lab in America, and another is in a commercial industrial lab. And none of them actually could meet the requirement of efficiency yet, and that's why
Mm-hmm.
you don't see commercialization. So, but we believe that we will be able to do that. Yeah.
Certainly, you will. So beyond EV charging, this technology also holds promising promises for application in next generation data centers, wind energy,
Absolutely.
yes,
Absolutely.
railway
Absolutely.
traction by enabling
Yes.
high efficiency power conversion.
Yes.
Directly
Yes. 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 Yes.
elaborate
Absolutely.
on this as well.
Sure. See, what happens is today in the data centers, as you know, because of this AI and cloud computing, right?
Mm,
The say, for example, if you do a Google search and if you do
mm,
the same thing on ChatGPT, probably the amount of computation that it is going to do is much higher compared to the regular search, right?
mm,
So what's happening that you have got this GPUs, right, which is like Nvidia is one of the pioneering company which is
mm,
making this GPUs where the AI algorithms are being run, right? They are severely power hungry, right? So the data center power is it is taking seeing a quantum jump in the
yes.
amount of power. So again, the same story holds that if the power is high, then it will come as a medium voltage to your place.
Mm-hmm.
And today, what happens is again, there is a step down transformer which actually takes power from at 11 kV, and then you have that switch yard and that kind of stuff, and then it is stepped down to 400 volt, and it goes inside. And then it has a long run that 400 volt after it is being stepped down outside, right? It goes inside the building, and inside the building you have this power conversion going on. So one study estimates that we lose about 2 to 3% power in that low voltage run that is happening from outside to inside the building. Now the thing is that if you can actually have this technology which actually converts the medium voltage directly without this, then what happens is that you can actually put your conversion inside the building itself. You don't need such a big place because it is
Mm,
so small, right? And you go to low voltage, you directly take 11 kV, go to low voltage, and serve the power, give power to your racks in the
mm.
server power supply. So that's the concept, and people are working on it, right?
Right, right. So, sir, are
And
there, please continue. There's,
no, no, go ahead, go ahead.
so, are there IP protections or licensing plans for broader adoption outside India?
Yeah, see, the thing is that if you actually notice that right now with Delta, we have a number of patents
Hmm.
which has been applied. Few of them are currently being applied to other countries other than India,
Mhm.
and there are many in the pipeline. Yeah, because it's a cutting edge technology.
Right, exactly.
There are a lot
And
of innovations. Yeah. Mhm.
and how does this work align with India's national EV policy and charging infrastructure goals?
Yes, absolutely. So, some time ago, we did we did a conference. It was a international conference that happened in Bangalore in power electronics,
Okay.
and there I we invited actually. I don't know whether I can tell his name,
Mhm.
but he is from the National Highway Mission, and he's from the because government of India has this NHEV, I think it's a initiative,
Mhm.
and it is headed by the by a wing in government who who does this ease for doing business, right? The
Mhm.
government help for ease for doing business.
Yes.
So I met that gentleman, and he told me that essentially India would like to rapidly increase its national highways has to be powered by EV
Mhm.
charging stations, high power charging stations, which can also connect with the wind and the solar, which our invention again enables that because of the multiple ports that
Mm.
you get. So the thing is that this technology, if it comes up, we were talking about that, and we also have a stall. And actually, I'll tell you, you would like to also come to PCIM that is going to happen in Delhi in December. If you in contact with me, I can also introduce you to. This is one of the largest power electronic converter exhibition, mostly focused on industry. We are also going to have a stall there from our lab. So we had a stall there, and then he saw that technology, and then he said that this is really promising, and if we can bring this up very soon, then we can save on a lot of copper and iron cost, and also energy, right?
Mhm.
So, and I know that Delta is one of their. I think they are connected. I exactly don't know, but I think they will play a role in electrifying with the charging stations of our highways. Yeah.
Okay. And in your views, what does an ideal fast charging network in India look like in 5 years?
See, what I think is that in 5 years, you should be able to get like how it is the petrol ones. But
Mhm.
in my understanding, I believe that it will be possible that you will be able to charge your vehicles in 10 minutes or less than 10 minutes,
Mhm.
right?
Okay.
And the thing is that the way rapidly things are growing, I think you may need to top up, because you will be always a little bit charging at night at home, and
Mhm.
all the parking lots and all that. So the thing is that you see, it is like this. Remember when the smartphones came, we understood that we need to keep it plugged in at night, right? So that you don't end up losing charge for the day. Initially, this is going to be like this: little bit you charge at home, little bit you charge at your workplace, and
True.
then you have the opportunity charging everywhere, right? So with that, we'll be able to go on. And I believe, yeah, what happened to the smartphones, right? See, now you have fast chargers.
Mm.
You just plug in a coffee shop, you are done in 15 minutes, you're charged, right? So I think we will reach that stage probably in 10 years. That's
Okay.
what I think. Yeah, yeah.
And what excites you about this technology's long-term impact on power infrastructure?
Yeah, because you see, the thing is that if you look at power electronics, right,
Mm.
it is there in both, in the generation and also in the consumption place, right? So the thing is that if you can, so say for example, if you use solar, wind, everything requires a power electronic converter to,
Mhm.
harvest that energy and put it on the grid. And anything like your laptop chargers, anything that you are using, like you see, we also in your AC, In your fridge, we have an inverter. There is a power electronic converter which optimizes the energy consumption. Like, see,
Right.
people talk about, you must have seen inverter based AC and all that, right? So the thing is that what I believe is that with more and more use of power electronics, both at your generation, renewable generation end, and also your consumption end, will have a dramatic improvement in the efficiency, right? And also in terms of the size of the converter, right? Which always makes life easy, like your chargers and all that. So I believe that this technology has that promise that we can go fully renewable
Mm-hmm.
with a minimum carbon footprint. Yeah.
Right. And I forgot to ask you one question. What is the environmental benefit of integrating local storage and renewables into these stations?
Yeah, see, the thing is that if you look at the problem, right? The problem is the greenhouse gas. If you are using thermal power plants, right? If you are relying on them, so the whole idea of electric vehicle is that you will not use petrol
Mm.
that pollutes, right? That gives you these greenhouse gases and all that, along with nitrogen and all of that, right? So now, if you are charging your electric vehicle or the battery, if you are using something energy that is generated using a thermal power plant, right? Then it is not serving the purpose. You are just moving pollution from one place to another. Of course, it helps. The pollution helps with the pollution in congested Indian cities, right?
Mm.
But if you see the totality, your carbon footprint, you are not reducing it as such. But if you can seamlessly, connect all your renewable resources and also charge your vehicles using renewable energy,
Mm.
that is the win-win game. I mean, that is the game we would like to play, or
Mm.
leave our next generation with that, right?
Yes.
Yeah.
And in the end, anything significant you like to mention as your closing remarks?
No, I think one thing that I would like to say is that, because, um, okay, this may be a little different from what we are discussing, but
Okay.
whenever I think that people like you who has the outreach to reach to, our friends and the citizens, so there I would like to say this, that actually in India, because
Mm.
of this Atmanirbhar Bharat and, all that is happening, more and more it has become important or becoming important that we rely on indigenously developed technologies.
Mm.
And so, and see, that is one aspect. And of course, because of the climate change and all that, if we our time window is very small and we need to run and fight, right? So we actually need a lot of our very intelligent our young people to come into engineering, particularly electrical engineering, right?
Mm.
And participate in solving the problems, right? Because I think, at usually in our country, at after your uh, higher secondary, right? You decide which school to join, whether you will do an MB, whether you would go this engineering, that, and all that, right? And that time you don't have much idea of what's happening, and what is popularly there is all AI, ML, and all that. I mean, those are very important. Do
Mm.
those also, but also do engineering, right? So there is a lot of scope, lot of challenging problems are there, and one can have a quite rewarding career now in engineering. I mean, in
Mm.
engineering now we have to innovate, and we are not talking about just doing services, right? Service is okay, may not be very exciting for many folks, but here we need to innovate and we need to work, we need to fight, right? So somehow this message is not going to the parents who
Mm.
decide for their kids when they're like 16 or 18, right? So we would like that to happen. It's very important,
Right,
right?
right. Thank you
Yeah.
so much, and thank you for your time. And